Hello and welcome. We're going to discuss nuclear physics today. I think you are going to remember a lot of this from your chemistry class because it turns out that nuclear physics and nuclear chemistry are pretty much the same thing, but you probably don't remember the details anymore, so this is a good opportunity for you to refresh that. And let's start off by talking about what a nuclear reaction is in the first place. The nucleus of the atom, where most of the mass is contained, which consists of two types of nucleons, the proton and the neutron. These are the particles you are going to find inside the nucleus. Now you notice when I write a proton, I put a plus sign in a superscript there, and for the neutron I put a 0. That's because the proton, as you recall, is positively charged, and the neutron is not charged. It's neutral charge. The idea of nuclear physics is that, or nuclear chemistry, if you want to call it that, is that sometimes the nucleus undergoes changes. When most of chemistry is dealing with changes in the electrons in any given atom, the moving of electrons, the bonding of electrons, the location and energy of the electrons. But in the nuclear side of this, we're actually talking about changes to the nucleus itself. It's a far more rare reaction, but they do happen. And we're going to see if we can understand a little bit about it. Now, one of the things that's important is, remember how we learned a new unit called the electron volt, because it was a very convenient unit for energy at this level. Well, the masses of protons and neutrons are quite small. We are going to come up with a more convenient unit for those things as well. And that unit is called the atomic mass unit, or in some cases the AMU, but honestly most of the time it's just abbreviated with a U, a little baby U. Okay, so if I say I've got 1 U, that's 1 atomic mass unit, and there is a certain amount of mass associated with that, and that number is 1.67 times 10 to the negative 27 kilograms. Now this 1.67 times 10 to the negative 27 kilograms it corresponds to 1/12 of the mass of an atom of carbon-12, and which has 6 protons and 6 neutrons. So it's, in a sense, it's an average mass for a particular atom. You say, why don't you just make it something like the mass of a proton or the mass of a neutron? And the answer is, crazy enough, is that the mass of a proton and neutron are not fixed. The mass of these nucleons changes depending on whether or not it's in an atom, and what kind of atom, and the size of the atom, which brings us to the idea of what? The mass changes? I thought the mass was the amount of stuff. Well, it turns out it's more complicated than that. When we were learning basic physics, that was a great supposition, and it was worth sticking to for a while, but like in a lot of things in physics, as you get deeper, it gets a little more complicated. If we were to fully understand this, we say, well, how can the mass change? What is it changing into? What is it changing from? Where does that mass go? And the answer comes from a very, very famous equation, very associated with Albert Einstein, that says that the change in energy in this situation is equal to the change in mass times the speed of light squared. There it is, E equals mc squared. You knew you were going to see this at some point in physics, right? Most famous equation in physics, and now you see it. But you notice the deltas. So what this implies is that the change in mass is equal to a change in energy, and that the speed of light squared is a constant that relates them, which is insane if you think about it. How does the speed of light have anything to do with the conversion of mass to energy? Well, it's a strange universe, friends. One of the things that might be interesting to know too is, well, how much energy is involved in changing a particular amount of mass? Say, for instance, an entire atomic unit of mass, if that were converted to energy, how much energy would that be? And that's a great question. I'm glad you asked it. Well, here's the answer. The answer is that 1 atomic mass unit converted to energy is equal to 931 mega electron volts. It's actually 931.5 mega electron volts. Yeah, we'll go with that. All right. Anyway, so what are we going to do with this? Well, one of the things that we're going to learn about is what I talked about when I said that the protons and the neutrons change their mass when you combine them together to form the nuclei of atoms. If you can picture even this carbon atom that has 6 protons, and 6 neutrons. Yeah, like I said, I'm no artist, but if you imagine all these protons hanging out together inside this nucleus, imagine the electrical repulsion we're dealing with. Think about Coulomb's law. The closer things are together, the bigger the force. And the size of an atom is quite small. It's on the order of 10 to the negative 15 meters. That is a tiny, tiny compacted space with positive charges repelling the heck out of each other. And something's holding it together. Okay, that thing that's holding it together is called the strong nuclear force. And the strong nuclear force is associated with the neutrons. So the neutrons are they're the glue that holds the whole thing together. And they're the carriers of the strong nuclear force. But that requires energy. Imagine this is a clear example of a lot of potential energy. This repulsion is like a loaded spring, but a very, very tightly compacted, powerful spring. And something's holding it back, and that is energy. Because if somehow one of these were to get loose, it would clearly turn that potential energy into kinetic energy. And so the energy that we're talking about is called the binding energy, because it's binding it together. And that binding energy comes, in a sense, from the loss of mass of these protons and neutrons when they come together to form the nucleus. That's where the energy is coming from. So one of the things that will happen, if you're trying to calculate the binding energy, you would talk about the change in mass of the associated with putting all those components together to form that nucleus. One of the things that we do know quite well is the mass of a proton and a neutron when they are absolutely free and clear from a nucleus. So the mass of a proton in AMU is 1.0078 U. And the mass of a neutron, slightly more, at 1.0087. Now, if that's not a recipe for confusion, I don't know what is. I can never keep straight which one's which. I can, because I've been doing this a long time, and I know that the proton's just a little bit smaller, so I remember that. If you want to figure out what this binding energy is, you're going to take a nucleus and figure out what or you're probably going to be given the mass of a nucleus. And what you can do is compare that mass of the nucleus to the mass of the protons and neutrons. Were they separate, you'll find that there's a difference. You'll find that the collection of protons and neutrons, if they were separate, would actually have more mass. So there's a loss of mass when they bind together to form a nucleus, and that loss of mass is associated with the energy that binds it together. So we lost some mass, but we gained some energy. I want to just take this at this point and do an example so you can see what you're supposed to do. All right, let's find the binding energy of boron 10. Now, I hope you remember from chemistry that when you write an element in this form, that the bottom number is the number of protons, and the top number is the total number of the protons plus the neutrons. So you can do a quick little bit of math to figure out how many neutrons you have. If the top number is the protons plus the neutrons, and the bottom number is just the protons, if you subtract the two, you got the number of protons. So in this case, we have 5 protons and 5 neutrons. And we know the mass of the nucleus is 10.811. So the change in mass, which by the way is often called the mass defect, and don't think of it in terms of a defect like something is defective. Think of it more in the terms of defect like a defector, like somebody who left and some of the mass left, right? So defected. I don't know why. but I accept it. All right, and the delta mass is the mass of the nucleus minus the mass of the nucleons. So let's set this up. The delta mass is going to be the mass of the nucleus, 10.811 U, minus, and I'm going to make a big bracket here because we've got some things to do. We've got the number of protons times the mass of a single proton, plus the number of neutrons times the mass of a single neutron. And now it's calculator time. All right, so we'll plug this in the calculator and see what we get. Okay, let me tell you a little story about a man who was not properly prepared to do an example problem. That would be me. Okay, I wrote down the average mass of boron, something straight off the periodic table, which is an average mass between its two isotopes, which is boron-10 and boron-11. And boron-11 is actually the one that's more common. So the mass of boron-10 is actually 10.013. You know what, guys? I make mistakes sometimes. I know it's a shock, and you would never believe it, but it's true. There we go. Now we're happy. I was concerned because the value we got for 5 times 1.0078 plus 5 times 1.0087 was far, far less than the value I put up before, and that's not the usual case. This is usually going to come out to a negative number, and now I feel like we're on to something. So the value for all that bit in the parentheses is actually 10.008. Again, let's get the calculator involved, and we will find that we have a mass defect of 0.0695 U. So that's how much the mass changed. Now we want to know the binding energy. And last time I checked, mass is not energy. Well, it kind of is, but we would like to express it in a unit that is a recognized energy unit, like electron volts. So I'm going to do a conversion now. So if I take 0.0695 U and do that conversion, remember 1 U is 931.5 mega electron volts. Calculator says 64.7 mega electron volts. Now you could convert this to joules if you wanted to, but it's not really necessary for this example. Now that's going to conclude this video, and there will be another video that will cover the rest of this stuff. So I'll see you there.